So let me again clarify what we have made. We have obtained the following thing. At the beginning of this lecture, we have introduced a pseudo-tensor, T mu, energy momentum pseudo-tensor for the gravity, such that we have the following conservation law. And this guy has this tedious expressions through the components of the metric tensor. At the same time, after that, we have considered linearized perturbations in flat space-time. So we have considered flat space-time plus perturbations on top of it. In this approximation, Einstein equations acquire the following form: 16 pi kappa, exactly the same T mu nu plus T mu nu, where this guy expresses linearized perturbation. So psi mu nu is just traceless part of H. So it's just H mu nu minus 1/2 eta mu nu times H, where H is a trace of H mu nu. So this is just linearized part, and this guy contains nonlinear part of the metric tensor. So nonlinear part. Nonlinear part describes the energy flux. So now we're gonna consider this equation. This equation, in a sense, is very similar to the one we have in electromagnetism, where we have the following situation: 4 pi over c yacht mu in appropriate gauge. And we want to consider free gravitational waves. Free electromagnetic waves are obtained when the right-hand side is 0 here, and free gravitational waves are obtained when this part is 0. So no sources for the gravitational waves. And we're first going to solve the equation with the right-hand side equal to 0, and then we're going to consider this quantity for the gravitational waves. That's what we're going to do now. Now, similarly to this situation, we want to look for the solution of this equation, psi mu nu equals to 0, so we solve this equation. We want to consider the solution of this equation in the following form, that H mu nu of x is just real part of epsilon mu nu times exponent minus ai chi alpha x alpha. For this, to solve this equation, here epsilon and k are some constant quantity. They're x independent. K is real, epsilon is complex. So for this quantity to solve this equation, k should, if we just plug it here, we obtain that k alpha times k alpha should be 0. Well, this is just the consequence of the application of two derivatives on the exponent. And also k mu epsilon mu nu minus half k nu epsilon mu should be 0. This is the consequence, this equation is the consequence of gauge condition. I remind you that the gauge condition, the condition in which we have obtained this or this equation, is as follows. It's d mu times psi mu nu should be 0. So from this equation we have this. If we plug this here, we obtain this equation. Now we're going to solve these two equations in some particular frame. Let us choose, well, this equation just says that we have a light-like, this k is light-like, which describes waves propagating with the speed of light. And so we want to choose such a frame, coordinate frame in space, such that k alpha is just k 0, 0, k. If we plug this vector into the exponent, we obtain the following situation. The exponent just acquires the following form. It's k z minus t minus z, which describes a wave propagating along the third direction with the speed of light. So we just plug it here. Now, using this vector k, which solves this equation, we want to solve this equation. This equation we have for each nu, we have equation, nu 0, 1, 2, 3. So for nu 1 and 2, for nu 1 and 2, we have the following from this equation, for nu 1 and 2, we have the following situation that epsilon 0, 1 is equal to epsilon 3, 1, and epsilon 0, 2 is equal to epsilon 3, 2. At the same time, the sum of nu equals 0 plus nu equals 3 components of this equation for this vector implies that epsilon 1, 1 plus epsilon 2, 2 equals to 0. After this, using these equations, already obtained the relations between components of this epsilon tensor, which is a polarization tensor for the gravitational wave, nu equals 0 component of this equation implies that epsilon 0, 3 is equal to 1/2 epsilon 0, 0 plus epsilon 3, 3. Now, let us perform. Remember that this equation was obtained in this gauge, but there is a remaining gauge freedom that we can transform. We can transform h mu nu according to the law h mu nu plus d mu epsilon 0 nu, such that epsilon 0 nu solves the equation that box of it is equal to 0. So it's a harmonic solution of the box operator. So now, then, the solution of this operator can be represented like this. The solution of this equation can be represented like this. It as minus I epsilon nu, well, this is a function of x, but this is already constant, real part, of course, of this quantity, minus I k alpha x alpha, where k alpha solves this equation. So we represent it like this. It does solve this equation if k alpha obeys this quantity, obeys this relation. So under such a transformation, epsilon mu nu transforms like this. Epsilon mu nu minus k mu epsilon nu minus k nu epsilon mu. Well, this is just the transformation law for this epsilon. Now, if we choose that epsilon 1 is equal to this epsilon 1 is equal to epsilon 1, 3 divided by k of this epsilon, of epsilon mu nu, of this epsilon. And epsilon 2 is equal to epsilon 2, 3 over k, and epsilon 0 is equal to epsilon 0, 0 over 2k, and finally epsilon 3 equal to epsilon 3, 3 over 2k. So if we fix this epsilon through this components of this tensor like this, as a result we achieve the following goal, that epsilon 1, 2 bar, epsilon 1, 3, sorry, bar, is equal to epsilon bar 2, 3 is equal to bar epsilon 0, 0, and equal to epsilon bar 3, 3, and all of them are equal to 0. As a result of these all relations, we have the following situation, that polarization tensor, which is this quantity, has the only non-zero components as follows, that epsilon 1, 1 bar is equal to minus epsilon 2, 2 bar, and epsilon bar 1, 2 is equal to epsilon bar 2, 1. These are the only non-zero components of this tensor, and they have these relations. So we are looking for free gravitational waves, so we are solving this equation with psi mu nu equal to h mu nu minus traceless part of h, basically. And we have been looking for the solution of this together with the gauge condition. The gauge condition is that d mu psi mu nu is equal to 0. And we have been looking for the solution of this equation in the form a real part of epsilon mu nu, where this is a tensor, complex tensor, minus I k alpha x alpha, and k and epsilon are constant, x independent. K is real, epsilon is complex. So what we have found that after fixing this gauge and using remnant gauge transformations due to harmonic solutions of box operator, we have found that this tensor has the following non-zero components, that epsilon 1, 1 is minus epsilon 2, 2. We we do not use a bar on top of epsilon, so we consider already the concrete gauge and omit the bars. 2, 1. As a result, we have the following situation, that the metric tensor, the metric for these gravitational waves, has the following form. So it's a linearized solution of Einstein equation. These are linearized approximation to the Einstein equations in the vacuum. 1 plus h11 dx squared minus 2h12 dx dy minus 1 minus h11 dy squared minus dz squared. So this form follows from the fact that due to this, these are the only non-zero components of this tensor. So the only non-zero components of this guy are 1, 1, 2, 2, 1, 2, 2, 1. As a result, curvature of the metric is as follows. So we have the following picture, basically. So in space coordinates, so if this is z direction, this is y, and this is x, we have a gravitational wave which propagates along this direction, along z direction. This k is directed along z, I remind you. And what it does affine transformations over the transversal directions. The reason for that is the following, that h11, if we plug this here, and keep in mind that this guy is complex, so h11 is equal to modulus of epsilon 11 cosine of k times z minus t plus phi 0, and h12 is modulus of epsilon 12 times cosine of k times z minus t psi 0, where these are the initial phases which are hidden in these complex quantities. So this stands here. So this guy solves linearized approximation to Einstein equations, and what it does, it describes the propagation of the wave which are finally transformed. So it's like compresses one direction for appropriately chosen. If we choose phi 0 equal to 0 and psi 0 equal to pi over 2, this is a picture we obtained that. It's like half a period, like goes along this direction, compresses in one direction, expands in the other, and then compresses in this direction and expands in the which was previously compressed. And so this is a situation we have for the gravitational waves. Now let us see what happens with T mu nu. So we want to plug this quantity, obtained quantity, into so we want to consider deformation on the right-hand side. We want to consider T mu nu, which is, as we remember, is of order of h squared. So to find it, one has to use that tedious, complicated expression for T mu nu through the components of the metric tensor. And I remind you that there was G mu nu, comma, this kind of quantities. And in our linearized approximation, it's approximately valid equal to G mu nu, comma, alpha, which is approximately minus h mu nu, comma, alpha. So the only non-zero contribution to T mu nu, as follows from all these relations, is obtained, follows from the term like this, G mu alpha. One has to look for the expression for this T mu nu through the components of the tensor. G mu alpha, G nu beta, G gamma delta, G sigma psi, G gamma psi, comma alpha, G delta sigma, comma beta, and this is, in our approximation, is approximately equal to 1/2 h alpha, comma mu beta, h beta, comma nu alpha. As a result, the only component of the only contribution to T mu nu in this approximation is approximately, for the plane waves, it's approximately 3 p kappa h alpha beta, comma mu h beta alpha, comma nu. And for this particular wave, which propagates along the third direction and has this kind of form, the only component is T03. The only non-zero component of this quantity is T03, and it is approximately equal to 16 pi kappa times h dot squared 1, 2 plus h dot squared 1, 1. So this is dot means, remember that h11 and h12 are functions of this difference. Dot means just differentiation with respect to its argument. So what we have is that along the direction of propagation of the gravitational wave, along the third direction, there is an energy flux. That's exactly the point we obtain for the gravitational wave. Gravitational wave carries energy on top of the fixed background. So we have a background metric, flat metric, and we have perturbation of this. This perturbation curves space-time and propagates with the speed of light and carries energy, gravitational energy, along the third direction. That's the reason we call this as gravitational waves, and that's what they do.